Hi everyone, my name is Yushan Zhang and I'm currently a PhD candidate from Lehigh University. Today I'm going to briefly talk about our work, efficient pre-trained features and recurrent pseudo labeling in unsupervised domain adaptation. Here is my outline. I will go through my slides from these 6 directions. So first of all, I will give you guys a brief introduction of our paper. As we know that we are in a big data era and there are different types of data. However, most of data are in original elementary form and they are not labeled. We also know that it is time consuming and expensive to manually label data right. Therefore, model reuse based on labeled data is necessary. However, because the problem of dataset bias or domain shift, some conventional machine learning algorithms will have lower accuracy in your test dataset. You may want to know why domain shift is a problem, right? So here I'll give you an example. For conventional machine learning, we usually assume that we will train our model use minister dataset, and again, we will test our model use minister dataset again, right? And guess what? We will get much higher accuracy, less than 99%. However, in the real case, we may train our model using minister dataset, while we may test our dataset use another new dataset, that's the Street View house number dataset. As we can see, there are huge difference between your training dataset and test dataset. We can expect a much lower accuracy of your test dataset, right? Another example can be we may train our model use USPS dataset and test our model using minister dataset. But in this time, since there are less domain difference between USPS dataset and minister dataset, we probably will get higher accuracy, less than 81%. However, it still has a lower accuracy than first setting, right? Another application can be image segmentation model. We may train our model use simulated image, and then we will apply that model use real images. And here is the output from your model. We probably can find that for some objects, such as the bus and the bicycle, they are misclassified, segmented, and also there are some shadings there. And we can observe that the accuracy is reduced because of domain shift, right? So therefore, domain shift is really a severe problem, right? So in the next section, we're going to formally define our problem, that is unsupervised domain adaptation. We usually assume that we have a labeled source domain and an unlabeled target domain. As you can see here, the YT is unknown, and our objective is straightforward, that is just train a classification model on source domain and improve the accuracy on the target domain. Also, there are many state-of-the-art methods, and there are 2 major categories. The first one is based on traditional methods, and the second one is deep learning-based methods. And due to the limited time, I won't cover the details of those methods. If you are interested, you can check the references. Although so many methods has been proposed, there are still several limitations. So for example, existing methods often extract deep features from one ImageNet model, let's say ResNet 50, and they did not explore other pre-trained networks, and also they did not select the best pre-trained features. Also, another limitation can be the noisy pseudo labels can deteriorate the domain invariant features across 2 domains. So how to improve the quality of pseudo labels is a problem. In order to solve these limitations, in our paper, we first realized some features from different neural networks, from AlexNet to EfficientNet B7. As we can see that the last neural network, EfficientNet B7, it has a clear boundary of different classes than the other 3 neural networks, right? Which means that to select a better represented features is important for domain adaptation. And however, most of previous work, they usually ignore this problem. So in order to solve this problem, in our paper, we proposed a model called the pre-trained feature selection and recurrent pseudo labeling. As you can see in this architecture, we first select the best pre-trained features from all 16 different neural networks. After we get extract features 5xs and 5xT here, and we put them into feature alignment process by minimize the MMD loss and the source domain loss, cross entropy loss. And then for the recurrent pseudo labeling, we keep generating those high confident examples from target domain and form the update label domain to replace the original source domain, so that we will learn more features about both source and target domains. In the next few slides, I will go to details of this different process. So for the first one, the pre-trained feature selection, as you can see in this equation, so we actually designed in an unsupervised fashion, which means that we can directly calculate the distance between the source domain and target domain, as you can see here. By selecting the minimum distance, we can determine which model can achieve the best feature among the 6 different neural networks. For the source domain, so it is usually cross entropy loss. And we also can make a prediction for the target domain, right, to get initial curse pseudo labels for the target domain. In the next process, that is recurrent pseudo labeling, an online question can be, how can we define the high confident example, right? So we actually take the probability of the prediction from the trained source domain classifier, so that if it is bigger than certain threshold, we will treat that prediction for the target domain as the high confident example. And then we form this new update domain, that XU and YU here, which is consist of original source domain and the high confident target domain here, so that we can further reduce the source domain cross entropy loss and MMD loss in T's recurrent pseudo labeling learning. And here is overall object function in our model. We also test our model using 3 different benchmark datasets: Office Caltech Chen, Office 31, and Office Home. We first to show how the pre-trained feature selection results. As we can see from the last row, our efficient net B7 achieves a minimum distance MD here among all 3 different datasets, although it takes a longer time to extract features, but finally it will lead to much higher accuracy. Before we talk about the accuracy, we also conduct a parameter analysis. So we have 2 different hyperparameters in our model. That is T, the number of recurrent learning, and the PT, the number of the threshold. As we can see that if the T equal to 7 and the PT is equal to 0.5, 0.8, and 0.9, the edge divergence achieves the minimum number, which means that those 2 parameters are the best for our model. So here is the details of the accuracy. We can paste that to last row, as we can see that our model achieves the highest performance. And also for different recurrent learning from 0 to 3, the accuracy is increased. Right? And a similar trend can be observed in Office Home dataset and Office 31 dataset. We also conduct the Ablation study to show how different loss functions that MMD affect different recurrent pseudo labeling. As you can see from the results, with increasing of different number of iterations and MMD loss, the accuracy is improved, right? Finally, in conclusion, we efficiently and effectively select the best pre-trained features among 17 well-trained ImageNet models in an unsupervised fashion. And we found that the efficient net B7 model shows the highest quality in extract image features. We then propose the recurrent pseudo labeling to train progressively generate high confidence levels and improve the performance for the target domain. And that's for all my slides. Thank you. If you have any question, please feel free to email to us.